presentation under the title of Neural Network-Based Model Reference Adaptive Control for PVTOL aircraft with enhanced trajectory tracking. So, my lady, you have 10 to 15 minutes to present the essential of your work. Yeah.
Good morning. Good morning. My name is Safina Zounsou. Good morning. My name is Safina Zounsou. Today I will present our work on neural network-based model reference adaptive control for PVTOL aircraft with enhanced trajectory tracking. Our presentation will follow this structure. We'll start with an introduction to the problem, outline our key contributions, present the PVTOL model, detail the controller design, discuss stability analysis, share the simulation results, and conclude with conclusion. The PVTOL aircraft are fundamental UAVs. They are several. The PVTOL aircraft are fundamental UAVs characterized by significant theoretical and practical challenges. They are severe underactuated, means only two control inputs, total thrust and differential thrust, regulate 3 degrees of freedom. They also exhibit strong nonlinear coupling between rotational and translational dynamics, and high sensitivity to model uncertainties and external disturbances. While conventional control methods struggle with parametric uncertainties and model dynamics in real-world applications, model reference adaptive control is a valuable framework for handling system uncertainties by forcing the plan's behavior to track a reference model through online parameter adaptation. However, traditional limitations include challenges with rapidly time-varying uncertainties and non-parametric nonlinearities, which are critical in systems with strong coupling like PVTOL. This is where neural networks come in. Neural networks offer universal approximation capabilities, making them ideal for compensating non-nonlinearities and disturbances. By combining max stability guarantees with neural network learning capabilities, provides enhanced robustness against complex uncertainties. Yet, challenges remain in applying neural network enhanced to PVTOL, including interconnected control, architecture and stability guarantees through approximation errors. Our work makes 3 key contributions. First, a cascade control architecture with dedicated neural network compensators for each subsystem. Second, a composite adaptation law combining Lyapunov stability with neural network learning. And third, establishment of a framework which is extended to more complex area systems. Here we see the PVTOL system and its force distributions. The dynamics are characterized by a strong coupling between the roll angle and the lateral motion. We derived the equations of motion which were then decomposed into 3 interconnected subsystems for control design. Our controller design begins by decomposing the complex coupled PVTOL dynamics into 3 canonical state-space subsystems. This is achieved using small angle approximations to separate the raw, vertical, and horizontal dynamics. This gives us a cascade structure for controller design, which is composed of a nominal linear controller and a neural network adaptive compensator. For each subsystem, we define a reference model that specifies ideal performance. Then we design a nominal controller using model matching calculating gains. So the actual system behaves like this model. This gives us a stable baseline control. compensator to handle uncertainties. The neural network uses custom-based functions and updates the weights online using Lyapunov-based adaptation law. A critical part of our work is stability analysis. We use Lyapunov function candidate that combines tracking error and the weight error, estimation error. The analysis proves that both the tracking error and the neural network weights are uniformly intimately bounded, guaranteeing stable performance. Now, for the simulation results, we evaluate our controller in MATLAB Simulink on the numbers using parameters from a typical smart state platform. The state tracking performance was excellent across all degrees of freedom. The roll and wheel tracking was precise, and both the lateral and vertical positions showed smooth and accurate tracking, closely matching the reference models despite the coupling effects. The control inputs, which are the differential thrust and the total thrust, remain smooth and within reasonable physical limits. This demonstrates the practical feasibility of our controller for actual hardware implementation. Finally, the neural network adaptation performance was stable. The weights for the roll and vertical networks adapted quickly, while the lateral network took slightly longer. All weights remained bounded, confirming stable online learning without any parameter drift. In conclusion, we have successfully developed a neural network enhanced scheme for the PVTOL aircraft. It effectively handles under actuation, nonlinear coupling, and system uncertainties, with excellent tracking performance across all degrees of freedom with minimal error, and smooth visible control inputs within physical implementation limits. The Lyapunov-based stability guarantees with bounded errors and weights and neural network compensation for unknown disturbances and parameter variations. For future work, we plan to experimental validation on actual hardware extension to duty flight scenarios. Thanks for your attention.
I would like to thank the presenter for this clear presentation with a comprehensive English. Thank you very much. As always, I start off by asking the audience if there is any question. After that, I move to our colleagues. Yeah, wait, please. Yeah.
First of all, I would thank you for your clear and enjoyable presentation. As far as I know, that the PVTOL system is like the landing and the takeoff of the aircraft. So landing, vertical landing and takeoff. This is we consider that VTOL, if you know this word, VTOL also. Yeah. So I have a question about if you include the dynamic equation here. What you mean about the dynamic equation? It's like we all studied before. You mean about dynamic? It's like the singularity method in the aerodynamic system aircraft. So you mean by this, or because to control the aircraft landing is too hard, especially for the quad aircraft. You know, that's aircraft who has a lot of engines. It's like 4 or more than 4 engines. The quad, what we can call it the quad. So my question is, if you include and you take in consideration all of these equations, the dynamic, the singularity methods, or something like that. I want to understand that all. If you wouldn't mind, please.
We have all the complexity of dynamics as uncertainties. Okay, and we put as a solution this with model reference adaptive control to handle the uncertainties as a total uncertainties,
Yeah, we are.
as a function.
Yeah, we are in the same place, so what I understand before. So, because if you want to control an aircraft, it's not easy thing. So, you have to take in consideration the stability. So, before you go into how to control it, you have to know which is the problem.
Yes.
This
is why we use this PVTOL. PVTOL is a benchmark for the other complex systems, flight systems. Okay.
What I understand that the PVTOL inside PVTOL there is some parts responsible for the dynamics. Yeah.
It's like in drone. It's like a quadrotor. It's like it's
Yeah.
a benchmark.
Thank you very much.
Yeah, thank you very much, Professor Hajjaz Faisal. Any other questions for the audience before moving to my colleagues? No questions? So I will give the word to my colleague, Dr. Bouchard.
Merci beaucoup, Monsieur le Président. Donc, merci beaucoup pour la présentation. D'accord. Donc, j'ai une seule question. D'accord. Pourquoi utiliser l'équation de Lyapunov dans notre système?
For handle stability.
Diapositive 3. Non, zid. Yes. D'accord. Expliquez-nous l'équation de Lyapunov. Quel est le domaine de stabilité?
This Lyapunov function combines the tracking error with the weight estimation error. So it can guarantees the stability of the tracking error and the normal network together. Okay, in one step, in one Lyapunov equation, we can guarantee two things: the estimation error and the tracking error. We can guarantee that they are uniformly ultimately bounded. Not going to point d'équilibre, un seul point d'équilibre. They will not just equal bounded in the limits of stability.
Est-ce que vous avez utilisé comme référence, c'est-à-dire le step échelon, comme ça? Est-ce que vous avez utilisé l'entrée rampe?
Non.
Oui, donc merci beaucoup.
Maybe my other colleague have another questions. Yeah.
So thank you for presentation. My question is about of the use of the MRAC adaptive system combined with the neural network to control your PVTOL aircraft. What is the model used in your plant? The model reference in your presentation. Can you show it? You have used this model combined with the neural network to handle the stability of your system. Okay. Concerning the neural network, which kind of neural network you used in this case? How many hidden layer equation used here?
We use single layer neural network, yes,
So,
with 10 neurons.
the hidden layer,
One hidden layer with 10 neurons.
with 10 unit, the training gives you a good result.
Yes, excellent results as you see.
How many
We use training based on the adaptation law.
the percentage of your training you have reached in your
I didn't present it here.
you tell us the result, the percentage of your
I forgot because I test the
several
system, yes, in several conditions.
the best one, what is the result?
About 18, if I remember.
18.
Yes.
Okay. The weight equation, which kind of weight equation you use in this in your note? L'équation de poids utilisée.
Adaptation law.
Yes. The nerve.
Yes, it's based on the Lyapunov.
D'accord. Okay, thank you.
Thank you very much, Dr. Asaba Mohammed. Maybe I'll take the chance to ask a small question which is presented on the third slide. If you could show us. My small, no, other one, 4. No, sorry. 10, sorry. Yeah. Regarding the roll angle tracking, as presented in the red color is the reference maybe.
Yes, it's the reference.
So the blue one is the measured phase angle. Yes, that's true. Have you taken in consideration the physical limits of the other size response? For example, if I measure a value, I take in consideration the time response and the other size, plus or minus 5, for example. Because I'm not really sure that this response gives good results, if I can use the word. Because in measuring values, we always take in consideration the flickers, if you know the word, the harmonics, the problems related to signal variation. Is this oversized value given by the blue one acceptable regarding some specific standards or not? Thank you.
You mean the control input limits? Yes, we use the saturation limits for the control inputs. They are shown here. 10 minus 10. So that we can implement it in
Sorry, I'm aware about that, the saturation limit, but the saturation limit is in calculating the values, but the real values are oversized of the limit. You understand what I mean?
Yes.
Yeah. Maybe what are the limits of your system here? I'm asking about the real limit of the system. Yes.
Singularities, yes. Yes, we didn't consider here in the singularities condition. Yes, you are right. Thank you. Thank you for your observation.
Yeah, thank you very much again for another time.